expectation doesn't have to be only dollars. So for example, over here, the question is, what is the expected number of tails when flipping 3 coins? So in this case, our variable x is going to be number of tails. We want to know what is the expected value of variable x. So let's set up our XPX table. I don't think we need a results column for this one. So what we could get is we could get 0, 1, 2, or 3 tails when we're flipping a coin 3 times. And the probability, you can refer back to when we did probability distributions, is going to be 1 out of 8, 3 out of 8, 3 out of 8, 1 out of 8. So the XPX 0 times that is going to be bupkis. This is going to give us 3 out of 8. 2 times 3 out of 8 is 6 out of 8, and 3 times 1 over 8 is 3 over 8. And if we add all this up, we get 3 plus 9, we get 12 out of 8, which is 1.5, which kind of makes sense if you think about it. So if you flip 3 coins, the expected number of tails, which is x, is going to be 1.5. So we expect half of them to be tails. Will we actually get 1.5 tails? We will not, but we expect it. Expect the number of pips when rolling 1d6. That's kind of another way of saying what do you expect to get when you roll. What value do you expect to get when you roll a 6-sided die once? So x, p of x, x p of x. And we know that x could be 1 or 2 or 3 or 4 or 5 or 6. And this is a uniform probability, so it's 1 out of 6. 1 out of 6, not 2 out of 6, that's a 1. There's a 1 out of 6 probability of each of these happening. And if we multiply it, we're going to get 1 out of 6, 2 out of 6, 3 out of 6, 4 out of 6, 5 out of 6, 6 out of 6. We could reduce some of these, but that'll make it harder to add, because when you add, you're going to have to figure them and put them back into this form anyway. So you add them all up, and the sum is going to be 1 to 6 is 21 over 36. Which, not over 36, 21 over 6, right? It's 21 over 6, which is going to be equal to 3.5. So when we roll a 6-sided die, so if x is going to be the number of pips, then the expected number of pips, or essentially the average roll, is going to be 3.5. And that's the expectation when you roll a 6-sided die once. Okay. A bag is 7 red and 8 blue marbles. If 2 marbles are drawn at once, what is the expected number of red marbles? I'm cheating a bit here. What I did was I copied the example that I did before because I didn't feel like doing the math again. So this is copied from the probability distribution lesson. So I'm going to come up with, so x is going to be in this case. Oops, I'm doing that one. X is going to be the number of red marbles. And we're drawing 2 marbles. So the options are, we could, there's our x, p of x, x, p of x. So the number of red marbles, we could either have none of them, or 1, or 2. And from previously, the probabilities were 26.7%, 53.3%, and dead on 20%. If we multiply it as 0 times this is going to give us just 0. 1 times 0.533 is 0.533. 2 times 0.2 is 0.4. If we add these up, we get 0.933. What does that mean? It means we expect to get 0.93 red marbles. This is not a percentage. I'm not expecting to get 93% of something. It's not a probability. This is an expectation. I expect to get 0.933 red marbles. And I wouldn't round it either. That's what I expect to get. That's the expectation. So for example, if I said, what is the probability of pulling the expected number of red marbles? So what's the probability of pulling 0.933 red marbles? The probability that x is going to be 0.933 is, of course, 0. There is no chance. You're not going to pull 0.933 of a marble. But a different question, what if I said, what is the probability of getting at least the expected number of red marbles? So we expect to get 0.933, and so that's our expectation, and we want to get at least that, so that or more. And so the probabilities are going to be those two over there. So it's going to be 0.533 plus 0.2. So the probability that x is bigger, or equal, I guess, to 933 is going to be the 533 plus the 0.2, which is going to be 73.3%. So there's a 73.3% probability of getting more than 0.933 red marbles.